So in this lecture, we're going to talk about concavity. And I want to start first by showing some visuals. So take any 2 points. And these 2 points we can connect with a straight line. But there's other ways we can connect these points. Well, there's many ways, but with only one turning point, we could sweep from underneath like this to connect these points. Only one turning point. Or we could sweep around to the top. Now, with only one turning point, there's no other way to connect these. Now, of course, you can fill in all these spaces in between and make larger hoops like this. But the point being is the structure of your lines will either have this shape that kind of curves down, or a straight line across, or some shape that looks like it's curved up. And so these have names. If something is curved up, we would say that's concave up. Its concavity is concave up. And likewise, this top one we would say then is concave down. It curves down. And then, of course, the one here in the middle is just a straight line. So with derivatives, looking at our picture, we can make these statements, which is what you did in the past homeworks. If the derivative is less than 0, then we know the function must be decreasing. So all the places here where the line is sloping down, we know that the derivative here would be negative. It's less than 0. Likewise, if the derivative is greater than 0, we know that's a positive slope. So that means the function would be increasing, like in this spot here. The function's also increasing right here. And we can make this same statement with the second derivative. So the second derivative means taking the derivative twice, commonly called the second derivative. And I can make exactly the same statement, but with the second derivative compared to the first. So if the second derivative is less than 0, that means the derivative is decreasing. And if the second derivative is greater than 0, the derivative itself must be increasing. So what does that mean? Well, consider just a straight line, and imagine that this is a tangent line to some function. So if the derivative increases, then that means this tangent line is going to get steeper and steeper and steeper. That's what an increasing derivative would mean. The derivative itself, the slope of the tangent line is increasing. And for that to happen, your function must be curving up. And likewise, if we have a derivative that is decreasing, that would mean, imagine a tangent line, and then a tangent line would be sloping downward then. This would be a derivative that is decreasing. And to do that would mean my function must be curving down. As you can see, if this was the tangent line, then my function would have to be kind of sloping in like this then, have a concave down shape. And so these are our statements. The second derivative measures concavity. It measures the curvature that you have. So if your second derivative is 0, well, that's no curvature. If your second derivative is less than 0, then that means your first derivative is decreasing. And this would be concave down. And notice the picture over here. And let me draw in a visualization for the tangent. So imagine this line right here I'm going to draw. Imagine this line is the tangent line as we follow along here. So you're going to have to kind of mentally imagine that. But I'm going to move along this function from point to point. And what's going to happen to the tangent line? Well, the tangent line is going to start off steep like this, about right here. And then as we move along the function, the tangent line is going to decrease, the slope. And the slope will decrease, decrease, decrease. And then right as we get to the next point, it's going to be about like this, about right here. So that's the tangent about right there, right as it gets to the point. And so this decreasing derivative is concave down. And concave down is when the second derivative is less than 0. Now, if you can imagine this again, so imagine now we're going to go along the bottom line, and imagine our derivative right here is going to be like that, even though it looks like I did get a little curvature in there, but try to, well, I guess I can kind of mimic that. I guess we'll make it look more like that. So starting at this point, what's going to happen to the tangent line as we follow this function along on the bottom? Well, if you look, if we follow along, the tangent line, the slope, is going to increase. And then right as it gets to the end point, it's going to be looking about like that. So when the derivative is increasing, we get this concave up shape. And when the derivative is increasing, that means the second derivative must be greater than 0. So I want to go back to the graphs we saw in the last homework, just so we can connect that with concavity. So I really wish I could move this line and change its orientation at once, but I can't. So you're going to have to imagine this a little bit in your head. But here's my tangent slope. And as I follow this function along, this tangent, as I move it along, is going to be increasing. So right here, it's going to have that shape. And as we move along, so right at the top, of course, the tangent line will be horizontal right at the top. And as we move along the function, it starts to slope down. And so the derivative is decreasing. And so we get a concave down shape as we move along. But if I keep moving along here, say we get to this point right here, the derivative starts sloping up again. And that's because we've changed concavity. So on our first hill, we encountered concave down because our derivative was always decreasing. But at a point about right here, that changed. And then the derivative started to increase again. And as we go around this valley, it's pretty clear then now the derivative is definitely sloping up. And so there was some point where that changed. And so what we would say here is this first hill is concave down, and this valley here is concave up. Here's another problem we did. This is just a standard parabola, and it's all concave down. It's everywhere concave down. Here's another one we did in the last homework. So if we look at this one, this is concave up. So a valleys are always concave up. Hills, concave down. Another valley, concave up. So this function changed concavity twice. It was concave down or concave up, and it changed once to down, and it changed twice back to up. Here's another one we did in homework. So starting at the left here, this is all concave down. And then a change happens right here at 0, and now it's concave up. This one we did. This one is all concave down everywhere. A little bit harder to see that curvature right there, but if you could zoom in there, you'd see it better. And the last one we did in the last homework, here's concave down, and then a change happens somewhere here, and now it's concave up. Now I've been saying some change happens here, and that change is the subject of this section. So let me just say again, concave down means the derivative is decreasing. So it's decreasing right here, the derivative. But then over here, it's increasing. And remember, decreasing means negative numbers, increasing means positive, and what's between negative and positive is 0. Which means somewhere here, there must be a 0 change in the derivative, because that's how you go from negative numbers to positive numbers. You got to cross 0 in assuming smooth functions here, no gaps and holes, and it's got to be continuous and differentiable and all that math stuff, which all our functions are here. So there's got to be some point between negative and positive numbers where there's 0. And this is the point we're going to now be looking for. We want to look for this point where concavity changes. And let me just paste that over here. So the derivative where there is 0 change occurs, so the derivative right here where there's 0 change, this is where the second derivative is 0. Remember, we're going from negative to positive numbers, so this point here must be where the second derivative is 0. And then these points we call inflection points. So you're going to try to have to pack this in your brain and find your own way to distinguish between these two things. But remember, the first derivative equaling 0 are critical numbers. The second derivative equaling 0 are inflection points. And they tell us very different things. So remember, the first derivative is about setting it equal to 0 is about extrema. The second derivative being equal to 0 is about inflection points. It has to do with concavity and curvature. And that's what we're going to be doing. Is we're going to be finding these inflection points, and the inflection points are what separate these concavities. What separates concave up and concave down. So let's check out a friendly polynomial. Polynomials are always friendly because they're straightforward derivatives. So we now want to get the second derivative. Now to get the second derivative, we have to do the first of first. So the derivative of x cubed, 3x squared. Derivative of minus 3x is minus 3. And the derivative of 3 is 0. So there's our first derivative. And the second derivative means do that again. So I'll just stick another apostrophe in there and take the derivative again. So 3x squared is 6x. And the derivative of minus 3 is 0. And so there is our second derivative. And now to solve for the inflection points, we'll set this equal to 0. because that's where the inflection points will be. And so we can solve that and find that x equals 0. Oops. Getting confused with my copy and paste buttons there. So just solving that, x equals 0. And there's our inflection point. So if you're feeling some comfort with derivatives, yes, it was that easy. We just did the derivative again and set it equal to 0 and solved, bang, there's our inflection points. So I do have a graph of this. Here it is. Here's the function we're looking at. And you can see from the left, we're concave down. It's all a change that's sloping down. And then a change happens right here at x equals 0. And then the concavity changes to concave up. So I know an analogy it's made in physics a lot is concave down can't hold water. So if you pour water on this, it all falls off. But concave up can hold water. So if you poured water in here, it all collected in right here in our little valley. It's not a perfect analogy, but if you need some visual, or I guess a mental image in your head and how to understand concavity, that's one analogy with water. So let's try another one. And we want inflection points. We want to know, where are the inflection points of this function? And we need the second derivative for that. And to get the second, we need the first. So the derivative of 1 is 0. The derivative of minus 9x is minus 9. Minus 6x squared is minus 12x. And minus x cubed is minus 3x squared. And that's our first derivative. We need the second, so we'll do that again. And the derivative of minus 9 is 0. Minus 12x is minus 12. And minus 3x squared is minus 6x. And that's our second derivative. Since we're solving for inflection points, we'll set this equal to 0. And we'll solve. So I guess I'll just move this to the right. Divide both sides by the 6. And there's our answer. We can take a look at what that graph looks like. And here it is. So starting from the left, this can hold water, concave up. And then a change happens right here. Where is this right here? It's at minus 2. So right here at in an input of minus 2, the function changes concavity and then is now concave down. And that's our answer. Check out another one. Now I'm picking this one because your book and my math lab do this, and I can't figure out why. So you will see this in my math lab, what I have written right here. So they have, x to the fourth minus 2x squared, and yes, you can factor x squared out of that and write it as like that. I mean, it's correct. I just don't understand why you would do that. Because we need the derivative. And if we're going to use this, that means product rule. And product rule is more work. Why choose more work when you can 100% get the right answer with less work? So I don't understand the logic there. I don't understand why I would choose a product rule when I can not use the product rule. So when you see that, if you can figure out a reason why they're doing that, I'd love to know. So we need derivatives, and we'll do the first derivative. So x to the fourth is 4x cubed. And minus 2x squared is minus 4x. And there's our first derivative. No product rule needed. And then we'll do it again to get the second. So now we would have 12x squared, minus 4. And there's our second derivative. Since we're solving for inflection points, we'll set that equal to 0. And then we'll solve it. Divide both sides by 12. So we'd have 4 divided by 12, which is 1/3. And then we have to take the square root of both sides to isolate x. And there we go. I can isolate just that. Stick the square root there because the square root of 1 is 1. And of course, we took an even root. And so even roots will always have a plus or minus solution. And there's our two answers. I do have to say something actually really quick about this as well. It's very possible that the answer in my math lab might want a rationalized denominator, if you remember that from algebra. So let me just say this really quick. Rationalized denominator means, or rationalizing the denominator means get rid of all roots here in the denominator. And you do that by multiplying by that denominator. So you would do that. And now you can write this as the square root of 3 over 3. So those are the same answers. They just look different, but they are exactly the same. Whichever you prefer, again, a completely subjective thing here, and whichever looks nicer to you, but I do think my math lab prefers rationalized denominators. So let's take a look at this function, and here it is, the one we're doing. And our minus root, or our minus inflection point, I should say, is going to be about right here. And then our positive one is over here. So if you look here, concave up, it changes right here. And now it's concave down for a little bit. And then it goes back to concave up. And where exactly did those changes occur? Well, that's what we just figured out. Of course, we got to do some trig. So let's check out this one. And the trig functions do have a restricted domain here because, you know, the sine and cosine, well, all the trig functions oscillate forever, so it's pretty common to give some restricted domain here. And we need the derivative. So the derivative of x is 1, and the derivative of sine is cosine. There's our first derivative. We need the second derivative, so we'll do that again. The derivative of 1 is 0, And the derivative of cosine is minus sine. So there's our second derivative. We're finding inflection points, so we'll set this equal to 0. And we'll solve. So how would you solve this? Well, like any other way, divide everything by minus here, because you can get rid of that. And the part that may be different, if you're not too comfortable with, is to get rid of sine. That's where you would have arc sine. Now, arc sine is also written as sine to the minus 1. So let me just be clear here in case you're a little rusty on trig maneuvers, is what we're technically doing is taking the arc sine or the inverse sine, which they both mean the same thing, there's different names. We're doing this to both sides. And the inverse sine of sine is just x. And so our answers are then where the inverse sine is 0. So now this is completely up to you because I have absolutely no idea how your brain is thinking about this stuff. But for myself, I actually find it easier to think with sine x equals 0 than I do with x equals the inverse sine of 0. And I don't know why. It's just the way it is for me. It's easier for me to understand where sine equals 0 because I can think right off the head, well, sine equals 0, at pi, at 2 pi, at 3 pi, 4 pi. And that's our answer. Our answers. Sine of x, when does sine of x equal 0? Well, sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. And so forth. And the dot, dot, dot. Always forget where that one is. There it is. However, we do have a restricted domain here. A closed interval, because the endpoints are included, from 0 to 2 pi. So 0 works. That's in there. Pi and 2 pi work. But 3 pi and beyond won't work. So I can actually get rid of the ellipsis here, the goes on forever symbol. And those are our answers. So let's take a look at that graph. And here it is. So it's basically a linear function that is oscillating around the linear line there. And so just starting from the origin here, we can see this is concave down. And then it switches to a concave up right here. And then it's concave down, concave up. So this is where the water analogy kind of breaks down, because if you pour water right here, it's pretty hard to see if it's going to collect right there. But that is a concave up shape and a concave down shape right here. And where is this change right here? Well, that change right here is at pi. So we can see 0 right here at the origin. 0 is where the first concavity change is on this closed domain right here. So it's concave up right here. Then it switches right at the origin. And now it's concave down. And then at pi, it switches to concave up. And then at 2 pi, which is about right here, now it switches to concave down. So let's check out another trig function. again on a restricted domain here. And to get inflection points, we need a second derivative. And to do that, we need the first derivative. So we do have a product rule here. So we'll have sine, and then the derivative of cosine. The derivative of cosine is minus sine. And then you add to that. Then we would add to that. I'm just going to copy this back here. The derivative of sine, which is cosine. And then the derivative of cos, and then we don't do any change on the second part there. So just to be clear, we did f and then g prime. So the derivative of the cosine gave us this minus sine. And then we did f prime. So the derivative of sine is cosine. And then g, which means do nothing, just the original function. So there's our product rule. And now we need the second derivative. And yes, the more complicated these problems can be, this doubles the work basically, because you have to take two derivatives now. So now you can see we're facing two product rules here. However, let me state that this is sine squared. Sine times sine is sine squared. And cosine times cosine is cosine squared. And this is, at least for me, a real challenge when I was first learning calculus. Because the trig functions, there's so many different identities with trig. And if you don't know those identities or haven't seen them, then how would you know to use one right here? Now, you don't have to use one. You do actually to get the final answer. But the point is, I highly encourage you to download the sheet that's accompanied with this lecture here in Canvas, where I list out all the major identities for trig. And whenever you're dealing with a trig function in calculus, you should try to remember in the back of your head, oh, you know, there's those identities. Do I need one here? And then pull out that sheet and look. Because a lot of times when you're using trig, those identities will be helpful. And if you do look on that page, you'll find there is an identity for this. And this equals cosine 2x. Cosine squared minus sine squared is cosine 2x. And notice that that makes life pretty simple for us here now, because the second derivative is just a chain rule now instead of two products. Actually, let me leave that there. Write another one for the second derivative. So the derivative of cosine is minus sine. And we have to take the derivative of the argument. So the chain rule here pops out a 2. And there's our second derivative. And then get inflection points. We'll set this equal to 0. And solve. So we can divide both sides by minus 2. And remember, and I know this can be tricky sometimes, but sine is a function, and these parentheses are connected to function notation. These parentheses do not mean multiply. This 2 will not factor out. In other words, I can't pull this 2 out because these parentheses are function notation parentheses. These are not multiplication parentheses. So it's very difficult to pull things out of function notation here. There are ways, but pretty challenging. And it's not just a straightforward factor type of thing. So what I'm trying to overall say is, this is the best we can do. This is our simplified answer. Well, I mean, our simplified equation. We can't get it any simpler. So I think the best way to deal with something like this is to redefine 2x. In other words, I'm going to call this y. And then I'm going to say that y is this 2x. Now, why do that? Because at least for me again, it's simpler for me to think, well, sine of what equals 0? And then I'll just figure out what these y values are. And then once I've figured out the y, I can then figure out the x. So what y values solve this? Well, that's the same thing we had last time. So when does sine equal 0? Well, at 0, at pi, 2 pi, and so forth. And that's y. And now we can solve for x. Oops. Got to change the text format there. Because we know y equals 2x. So we just equate these two. So if y is all this, then I'll just replace that with y. And now to solve for x, we'll divide everything by 2. So I'm going to divide everything by 2. So 0 divided by 2 is still 0. Pi divided by 2, though, is pi divided by 2. And 2 pi divided by 2 would be pi, and so forth. However, if we didn't have a restricted domain, we'd have to keep the ellipsis here. But we do have a restricted domain from 0 to pi. Closed interval, endpoints are included. So 0 works, pi over 2 works, pi works, but nothing else. And then there are our final answers for x. X is 0, pi over 2, and pi. So let's see what that graph looks like. There it is. So if we start at 0 here, 0 actually, you can see if we look to the left, the function is concave up. But to the right, it's concave down. And right at 0 is the inflection point. Now our next inflection point we got is pi over 2. So pi over 2 is our next x-intercept, actually, right here, where we switch from concave down to concave up. And our last inflection point right here at pi. And those are our 3 answers. 3 inflection points. There's something I want to mention here that's always true, but this problem I think it might be a little bit easier to see, is that for word problems, a common name for inflection point is the point of diminishing returns, especially in something like economics and money types of fields. Because if we start here to the left, and if we come along, now the derivative, remember it's concave up here, so its derivative is increasing, increasing, increasing And then right at the origin, the derivative no longer increases. Even though the function still continues up, the derivative is actually decreasing now. And so this is a point of diminishing returns. In other words, you're still getting an increase. So imagine this is profit. You're still getting an increase in profit. However, that increase is now slowing. And so the inflection point is also commonly referred to in context problems as the point of diminishing returns. You're not getting as much out anymore, even though you're still increasing, but that increase has now changed. Your function's increasing, but that rate is slowing. So let's check out another one, because we haven't mixed the log function into this yet. So let's try log. We need some inflection points, so we'll take a derivative. And the derivative here will be 2 will drop down, subtract 1. And there's just doing the straight up power pattern. But there is a chain rule here. We have to multiply by the derivative of the argument. And so derivative of log is 1 over x. I'm just going to clean this up a little bit here. So I'll just write this 2 log x here. Get rid of all that. And now we need a second derivative. So we have a quotient rule here that we'll have to do. And I'm just going to pull this off the side so you can look at this one over here, 2 log x over x. And we're going to do quotient rule on that. So that means we'll have the derivative of the numerator first. So that would be 2 over x. And then times x. Minus the numerator times the derivative of the denominator. The derivative of x is 1. All over the numerator squared. Now these x's here do divide out. And there's our second derivative. So we'll set that equal to 0. And solve. So remember, you can't divide by a number to get an output of 0. So there's no solution for this x in the denominator. There's no number that we can put in here that will get an output of 0. Can't divide to get an output of 0. So we can multiply both sides by x squared and get rid of it, since it'll contribute nothing. Divide both sides by 2. And let's just move the log to the other side. And then to finally solve, we'll raise both sides from base e, because that's how you get rid of a natural log, is to raise it from base e. You got to do that to both sides. Of course, e raised to the 1 is just e, and e raised to the log is x. And so that's our answer. X equals e. E being about 2.71. And let's take a look at that graph. Here it is. And maybe a little bit tough here to see, but the function is coming down, because I had to really zoom out here so you can see the curvature here. But if you could zoom in here, you see the function's coming down here, cruising along. It's concave up. It's still concave up, and then somewhere about right here, it changes to concave down. So it may be kind of hard to see because this curvature on the right side is not very large. It's a very small amount of curvature because it looks so straight there. But right here is an inflection point. And where is it at? It's at E. So about right here is an inflection point where the concavity changes. And it changes from up to down. And that's our answer. So I got one more here. Trying to pick ones that would look confusing. Log of cosine. No restricted domain on this one. So let's figure out the inflection points. Take the first derivative. We do have a chain rule here. So let me just pull this aside so you can see the log cosine over here. So the derivative of log is 1 over the argument. And the argument in this case is cosine. So the derivative of log is 1 over cosine. And then the chain rule will say we'll take the derivative of cosine, and the derivative of cosine is a minus sign. And just because I don't like the way this looks, I'm going to take the minus sign and put it over here. I'll take the sign and just stick it in the numerator here. And another thing that's good to know about trig is what is sine over cosine. Now, we don't have to say this equals tangent x. It's easier to, because you could do, because remember, we have to get the second derivative. And if we stick with sine and cosine, we'll have to do a quotient rule. So you can still get this, you can still get a correct answer. You'll just have to do more work to get it, if that's your thing. Not mine. If I can do less work to get exactly the same answer, then less work. Now, of course, there is value to doing the more work route because you can get comfortable with things, you know, practicing the quotient rule and stuff. So there still is value there if you want to go the longer route. We do want the derivative of tangent then, and that's secant squared. And there's our second derivative. And then to get inflection points, we'll set this equal to 0 and solve. So we'll do the simple thing first, get rid of the minus sign, divide both sides by that, multiply however you want to get rid of the minus. And we are left with a squared here. So I know that can be forgotten a lot with the shorthand notation, but this does mean secant squared. And you get rid of the squared by taking the square root of both sides. And the square root of 0 is 0. And so our final simplified equation to solve is when secant equals 0. Now secant, not a very common function, I guess is a way to say it. You don't see it a lot. And here again is knowing trig can help you here, is what does secant equal? Well, that's 1 over cosine. Now, why would you do that? Well, for me at least, because secant is a little bit unfamiliar, but cosine to me is very familiar, means it's easier for my brain to work with this part. And I can see, hopefully you can see as well here, that you can't divide to get 0. So there's something wrong here. And, well, I shouldn't say there's something. Well, I guess I can say equating this to 0 was a false thing to do because there's no solution here. So I'm being maybe a little bit technical in the wording there, but when we first equated this to 0, that is an assumption that the function can equal 0. We are assuming that to be true when we put the equal sign there. And it turns out putting the equal sign there was a false thing to do because there's no solution. So there's no inflection points. And what does this graph look like? Here it is. And these do extend down to infinity, all of these lines. Kind of looks like a bunch of pillars if you could fill that in. And you can see it is everywhere concave down. It never changes concavity. And we can see that we got no solution. We tried to solve for inflection points, and we couldn't find any. Now, this is the last thing to say here. All these open spaces, these are vertical asymptotes. So there are infinitely many vertical asymptotes here. And where do these vertical asymptotes occur at? Well, we can go back to our answer here. And these vertical asymptotes must occur where cosine is 0. Because you can't divide by 0. And cosine is 0 at things like pi over 2 and 3 pi over 2. Now, you don't need to solve for that for the homework. Just something extra I'm throwing in there. And these are vertical asymptotes. And we can also find their locations. So there's some examples on a variety of problems. I do encourage you to download the sheet I gave there for trig identities, the most common ones you're going to see. And lastly, all of the problems in this section will also want extrema. So I didn't do that here because I wanted to focus on just getting inflection points to making sure you understand how to get these inflection points, or doing my best to get that across. But all the homework problems do ask you for extrema. So all the stuff you've been doing with extrema, you're still going to have to do with these problems. And these problems will probably be the most time-consuming ones to this point, because you're going to have to do the first derivative, find all the extrema, and now do the second derivative to find all the inflection points. So try to give yourself some time on this one. It's all really good practice. And we got one more pure math topic to talk about. And then we will do all this then with word problems.